Okay. So looking at your operation sheet, okay, there are different operations that you can do with a matrix, just like we could with math. So if I have x plus y equals 2, and I have y plus 2 equals 4, and I wrote them like this on the board, could I also write them like that? Yeah, I just took what was on top and put it on the bottom. It doesn't matter what order I put them in. The same goes for matrices. We can switch orders for columns if they are asking us to. Okay, so for number 1 it says interchanging rows. It says interchange row 1 and row 3. So that means the numbers that you have on row 3, which are -8, -6, -7, and 1, would then be written here at the top. I know this is kind of small, but we're going to write -8, -6, -7, and 1 up at the top. And then we're going to write row number 1 on the bottom. Okay? So all we've done is simply swap the rows. That's what they asked us to do. Okay? We can also, in the same way that if we took an entire equation, so again, we're not learning new, we're just applying what we already know to a new form. If I take an entire equation and I multiply the whole equation by number 2, so now I have 2y plus 4 equals 8. Have I changed this equation? No, it's still the same because I multiplied the entire row by the same number. The same works for matrices. We can multiply an entire row by a number and keep the information the same. Okay, so number 2 says multiply a row by a non-zero constant. So if we multiply row 2 by -2, what numbers are we going to get? -2 times 4, and I did by 2 and not by -2 on there. It should be -8, -4, -10, and -16. You can see here I just multiplied by 2. Okay, we can also add a multiple of one row to another, or we could add 2 rows together. Okay, so in combining those steps, if I have my matrix here, and I say multiply the first row by 2, and then add 2 times row 1 plus row 2, and that's going to be my new row 1. I would say I'd have 2, 0, and 2. Now I'm going to take my new row 1 and multiply it add it to my row 2. So 2 plus 2 is 4. 0 plus 2 is 2. 2 plus 4 is 6. So now my new data entry is 2, 4, and 6. Right? So we can take the steps with our numbers, apply our same math rules to work through that. Okay. Okay, so operations when we start having 2 different matrices. There are some rules that we must follow. Right? If you are asked, are these 2 matrices equal? They must be equal in every single space. Every single entry must be identical. Okay? First, second, third, and fourth, the way that they order that in. When we think about entries, this is not on your notes, but it's good to write down. We will use this for the first one. I like to label my matrices. This is row 1, row 2, column 1, column 2. So if I'm looking at my first entry, it's row 1, column 1. My second entry would be row 1, column 2. Then I have row 2, column 1, row 2, column 2. So see how each entry has its own identification? So when we are comparing equal matrices, each entry point must be identical. It can often, they'll do this whenever they use fractions. They might, I mean, this is ridiculous, but they might do something like that. And then say, are these matrices equal? Yeah, they're equal. This one has fractions, this one does not. One might have decimals, the other might have fractions, another one might have integers in it. So as long as the number or the value comes out exactly the same, then they are equal. If they are flip-flopped, where they have the same numbers, but they are in different spaces, they are not equal. Okay? These are not equal because, as you can see, as we have labeled our entry points here, we're actually talking about two different entry sections. That's why they have to be in the exact same place. So if we look up here, we've got the first one is equal. All of our numbers in each of our spaces are in the exact same space, same number, same space. The second one, we have a flip-flop here on the bottoms. It is not equal. The third one, we have a 3 by 2 matrix compared to a what? How would we label these? A 2 by 3 matrix. So automatically I have a 3 by 2 compared to a 2 by 3. They're not even the same dimensions. So they cannot be equal. All right? So for addition and subtraction, if we have these two matrices, they will have a sign in between them, either addition or subtraction in the middle of them. And as we were just showing, as I was showing down here, that they have, each entry point kind of has its own label for where it's at. If I have x plus y equals, or x plus y plus 3x plus 4y, which terms can I add together?
Like terms.
Like terms. Okay, so I would add the x's together and then I would add the y's together because it's a like term. Same with a matrix, you can only add like terms. They are considered like terms because they are defined by, this is row 1, column 1, row 1, column 1. We could maybe call that x, like this could be spot x, y, z, t. You know, if you were to think about it as an individual variable, each space, each entry space has its own identity as a variable, right? So we can add like terms. If we are adding these together, the dimensions have to be exactly the same. So dimensions here we have, what is our dimension for this first matrix? It's a 2 by 2. Dimensions for the second matrix? 2 by 2. So our answer should be 2 by 2. See how these all match? Right? And we are going to add like entries. So for the first one, we can add all of our row 1, column 1. So 1 plus 1 is 2. And it goes in the row 1, column 1 space. Right? Now I have row 1, column 2.
0
is going to be 0. Right? And if we have our row 2, column 1, it needs to go in our row 2, column 1. I've got 2 plus 3.
5
It's going to be 5. And for our last space, we're going to have 3 plus 2 is 5. So when we've added these two matrices together, we have a new one. Has the exact same dimensions. We've added our like entries. Any questions? Okay. If you go back and look on the Google Classroom, you'll see I've color-coded them so you can see which numbers need to go together. Scalar multiplication. Scalar is a word, so if you have done, you go to print something that says you're scaling it up or you're scaling it down. It's just a number that refers to the size of something, right? So we can do 100%, 50%, whatever. So they use the term scalar to identify a number that looks a whole lot like this. Okay? What did we call this when we did 2 on the outside of parentheses, x plus y? What does this 2 do?
You multiply it.
Yes, you multiply it to every part. It gets distributed. Okay? Across. It has to go to every single part of it. Every single time. Right? So when we have a scalar, when we put a number in front, there will never be a little dot or anything for multiplication. It's just attached up at the front. Remember now that we're in algebra 2, like we're not doing the extra holding places. This means that this number, this 2, is distributed to every single part of the matrix. All right? So this is different than multiplying a single row. So in this case, our 2 goes to every number. We now have 2, 0, 4, and 6. The 2 would be distributed across to every entry point. Any questions about a scalar?